Let's begin looking at the nerve membrane as a way to move a signal. Um, so here you have your interior conducting fluid, your exterior conductive fluid, and if this were simply static, yeah, there's nothing going on other than you just charge this up and let it go, it would slowly discharge because there's leakage current, right? There's going to be leakage through the membrane. Um, And if you look at all of that in terms of what would be going on, it's a typical exponential decay. Um, the membrane resistance times the membrane capacitance gives you your time scale for this. And in this case, it's the dielectric constant kappa times epsilon naught, which is the permittivity of free space, times the resistivity of the membrane. And if you measure the resistivity of the membrane on the axon, you get around 10 to the 7th ohm meters. And so the time constant around 1 millisecond. So if things were static, as if there weren't any processes going on, there was no sodium, potassium pump, none of that, um, and you just were going to let things go, and there's not really any fluids here that are setting through the Nernst equation, setting a difference in concentration. Um, then this voltage is going to decay. And it's going to decay with a time constant about 1 millisecond. That means it's down to about a third after 1 millisecond, down to about a ninth after 2 milliseconds. And so that this is if things were static, but things aren't static. All right. And so if we were looking at this where things aren't static, there's your capacitance per unit per square meter. All right. Your change in voltage with time. So what is this term? Right. It's capacitance times change in voltage with time. It's the collection of charge in any given area. This is your current density. Um, in amps per square meter, this is the current leaking through the membrane. And this is a difference between currents on one side and currents on the other side. So well, it's the second derivative of the voltage, all right? But it ends up representing, you know, current differences between coming in and going out. So you've got current coming in, current going out, current leaking through, and charge building up, right? Charge building up. And so that's what all these three terms are: charge building up, current leaking through the membrane, the difference in currents from one side to the other. And this little cm is capacitance per square meter, B is the membrane thickness, A is the membrane radius, R sub I is resistance per meter in the membrane. And so, again, everything's happening around this membrane right here. And we look at that in terms of just passive spread. We got a leakage current that's some conductance times the difference in voltages, and conductance per square meter is your um, is sigma m, your conductivity per over B, right? And sigma m is 1 over resistivity. If you look at it in terms of that and put that back into the cable equation, you can rewrite the cable equation as with these variables, lambda squared and tau. So VR is your rest potential, V is your voltage you're at some other voltage. And so this equation has a couple of things in it that are very useful. One is lambda squared, or lambda is a characteristic length for what's going on. All right, so if you're looking at decays in terms of how quickly things decay in lambda, that's a characteristic length. Tau is a characteristic time for the time scales for things that are going on. And if you're looking at how fast this wave is propagating, lambda over tau is going to give you an approximation of the velocity of the wave, right? Lambda over tau, meters per second, right? And here, once you reach steady state, all right, no change with time, you can see V is just going to decay off in different directions. And if there are no spatial changes, we're back to, okay, the voltage is going to decay in time as things discharge, right? So this cable equation is exactly the same equation for the propagation of a signal down a telegraph line. That's why they call it the cable equation. And for many of the same reasons, same physical reasons you get here. Right? So this, not easy to solve. We're not worried about that right now. Not easy to solve. But your characteristics length and characteristics times, we can figure some of that out. Next, we're going to talk about the work Hodgkins and Huxley did.